Hi, Doctor. We are from Group 4, which will be presenting the topic of dilution problem using first ODE. I'm Jason Lee, the editor of this video, and these are my group members, Amil, Zia, Jericho, Sylvester, and Noha Adil. Let's start with introduction of first ODE.
My name is Sylvester Sim, and I'm from section 31. Today, our group will present the application of first-order ordinary differential equation in solving dilution problems. Dilution problems are commonly used in mathematics, chemistry, engineering, and industrial process to model how the concentration of a substance changes over time. Before we dive into it, let us know what is first-order ordinary differential equation. First-order ordinary differential equation, also known as first-order ODE, are equations that involving a function and its first derivative. First-order ODE have many real-life applications such as population growth, Newton's law of cooling, electrical circuits, and dilution problems. In this presentation, we are going to focus on dilution problems. So, what is a dilution problem about? A dilution problem studies how concentration changes when liquid flows in and out of a tank. In a typical dilution process, a liquid containing a dissolved substance, such as salt or sugar, flows into a tank, while the mixed solution flows out at a certain rate. The concentration of the substance inside the tank changes continuously over time. Dilution problems are commonly solved using the linear first-order ordinary differential equation method. This method is used because the amount of substance inside the tank changes continuously due to the inflow and outflow of the liquid. For dilution problem, the equation can be written as dq over dt equals to rate in minus rate out, where q represents the amount of substance in the tank. Before we start discuss the problem statement, we need to know what is the linear first-order differential equation. A linear first-order ordinary differential equation is a differential equation that contains only the first derivative of the dependent variable, and the variable appears only to the power of 1. It's called linear because the dependent variable and its derivative are not multiplied together and do not have power greater than 1. This type of equation is commonly used to model real-life applications such as dilution problems, population growth, cooling system, and electrical circuit. General form of a linear first-order ODE is dy over dx plus px times y equal to qx. And that's all from me now. I will pass to the next member to continue the presentation. Thank you.
So before I proceed my part, let me to self-introduce. My name is Jericho. So now, after we understand what is ODE, now we want to apply it in our real life. So it can apply in the dilution problem. So what is dilution problem? It involves a tank that liquid flow in and out, cause changing the amount of a substance. And the equation is dq over dt equal to rate in minus rate out. And qt stands for amount of substance in the tank, and rate in is concentration entering the tank times inflow rate. Well, the rate out is equal to concentration in tank times outflow rate. So this problem we can meet in our real life. So one of the real life example is medicine concentration in the bloodstream. So for example, patient receive medicine through an IV drip, while the body simultaneously remove it through metabolism and excretion. So we can use the first order ODE to find the drug concentration change with time in our body. For second real life example is fish tank filtration system. For example, fish tank continuously receive clean water, while all water is filtered out. So we can use the ODE to find the amount of waste in the water change over time. So next is an example question for this problem, which is tank initially contain 100 liters of pure water. Salt water containing 0.5 kg per liter enter at 3 liters per minute to the tank. So the mixture leaves at 2 liters per minute simultaneously. So we can use the equation just now to find the amount of salt water after pi t. That's all from me. I will pass to the next presenter. Thank you.
Hello, allow me to introduce myself. I'm Noha Adil, and today I'll be sharing with you the solution for this given example. So in order to start solving this example, we have to know what are the given variables and what are we trying to find. The given variables are the initial volume, which is 100 liters, the initial salt amount, 0, the inflow rate, 3 liters per minute, the inflow concentration, 0.5 kg per liter, and the outflow rate, which is 2 liters per minute. And we are trying to find the rate of change of salt over time, denoted as ds over dt. Now, as my friends explained in the previous slides, we can use the dilution problem to get the rate of change of salt per time or over time, which is equal to the rate n minus the rate out. The rate n is equal to the inflow of water times the concentration entering the tank, which is both values are given, so we're just going to use the values given, which is 3 times 0.5. It's going to give us 1.5 kilogram per minute. And now we have the rate out, which is equal to the outflow times the concentration in the tank. We do not have a value for this concentration, hence we have to find it. So here is how to get C, or the concentration of the tank. It's the amount of salt per water volume. So to get the water volume over time, it's equal to the initial volume plus the increasing rate of water. And we already have the initial volume value given, which is 100. And for the increasing rate, we can calculate it by saying that the water coming in minus the water going out times T is going to give us the increasing rate. Hence, we know that the water volume is equal to 100 plus T. So to get the concentration, it's the amount of salt divided by the water's volume. Since we do not know the amount of salt and it's going to be varying, hence we will just denote it as S. So it's going to be S all over 100 plus T. Now we will be able to get the rate out, which is equal to the outflow times the concentration in the tank. The outflow was already given in the question, which is 2 times S all over 100 plus T. And here is our rate out, which is 2S all over 100 plus T kilogram per minute. Now we will be able to set up our differential equation, and here it is. Now if we move the 2S all over 100 plus T to the other side, we can see that this equation looks like a linear equation, and hence we can solve it by getting the integrating factor, which is equal to the exponential e to the power of the integration of p of t with respect to t, which gives us 2 ln 100 plus t. And when we move the 2, it becomes a power, hence we have 100 plus t all squared. After getting the integrating factor, we can write up the equation in this form. The integrating factor times s, which is equal to the integrating of the integrating factor times q of t dt. By integrating the right hand side, here is what we get: 1.5 times 100 plus t all to the power of 3 all over 3 plus c. We move the 100 plus t squared to the other side. We divide both sides with it. Here is our ST equation, but now we have a constant c. So now we need to sub in the initial conditions, which is S0 is equal to 0. So at time 0, we had 0 salt. So after subbing it in, we can get that c is equal to negative 5,000, and we can sum it back into our equation to get the full S of t equation. And here is it. And that's it. This is our solution. Thank you for listening.
Hi, my name is Zaid Muzammil bin Jamaluddin from Group 4. I will discuss about the conclusion of our topic. So, in conclusion, our project discussed the applications of first-order ODE, especially dilution problems. We explained how first-order ODEs are used to model situations involving rates of change in real life. We learned that dilution problems can be solved using linear first-order differential equations because the rate of change depends on the inflow and outflow of substances in the system. By using the key equation, dq over dt equals rate in minus rate out. In our example, we analyzed a tank containing liquid with dissolved substances such as salt entered and mixed solution flowed out. Using the dilution equation and linear first-order ODE method, we were able to determine how the amount of salt changes over time. We also discovered that first-order ODEs are very useful in real-life situations such as medicine concentration in the bloodstream and fish tank filtration system. So that's all from us. Thank you.